Hi there, this is Dr. John, your physics and math professor, coming to you with another projectile problem. This time we have the problem of Leo the lion. I have written out the question there for you, but basically this is Leo the lion who's sitting on his perch, which is 4.5 meters above the roadway, and he sees a human transport vehicle coming along, and he decides to jump and entertain the passengers and see how they react. So he does a jump at 25 degrees to the horizon, 25 degrees up from the horizon at 8.5 meters per second. We want to know, what's his range? How far does he land from this straight up and down here to here? What's his horizontal range? Now, this is a fairly straightforward problem in projectiles, and the way that we usually start these problems is by taking the initial velocity, which in this case is a vector component 25 degrees up from the horizontal, and we would divide that into the horizontal component and the vertical component. Each of these acts independent of each other. Any force that acts on the horizontal probably does not act on the straight up and down, the vertical. Gravity only acts up and down. In this direction, there are no forces in this case, so whatever velocity you have in the x direction will continue on forever. The only thing that stops it is when the projectile, in this case the lion, goes to the peak, comes back down and lands on the ground straight up and down. That will end the motion and hence end the horizontal velocity as well. So how do you find the range? Generally with these problems, you find the time of flight, the time that the lion is in the air. In many problems, we start on the ground here, go up and come all the way down. It's sort of symmetric. In this case, because you're lifted up here, it's not symmetric anymore. It's a little bit harder. We're going to have a little bit more of a challenge to do that. So we're going to start off by redrawing this, the velocity, into vector form and seeing if we can find its components. Here I've redrawn this, the projectile going at 25 degrees from the horizon, and we have the two different components, the y component and the x component. In this case, the x component and the y component added up would be this vector component, but it's much easier if you move this vector component over here. So now we have this, which is the y component, vy, and this over here is the x component, and we want to find the different components. Now this looks an awful lot now, because this is a right angle triangle here. This looks like a trigonometry problem. If you remember, the sine of 25 degrees is equal to what? The opposite. That's vy over v0, the initial, which is the hypotenuse. And you can solve this just by taking this v0 and moving it over to here. v0, it's all multiplied like that. Erase it from here, and I have vy is equal to this. Let me rewrite this up here so we have it handy for in just a minute when we're going to solve for it. And then we do the same thing for this. This here is the vx. We're not concerned about the fact that it's in the negative direction or in the positive direction. We're just simply concerned about the magnitude, the size of these vectors. So to solve for this here, this would be like, for this angle, this would be the adjacent, this would be the hypotenuse. So in this case, we would have cosine 25 is equal to vx, the adjacent side, over v0, the hypotenuse. We can solve for this just by moving the v0 to the other side like this. And let's rewrite that right here as well. Now we've used up this triangle. We don't need it anymore. We should probably solve for these right away, because having these values of vx and vy will help us as we make progress in this problem. We'll start off by plugging these in. So vx is equal to 8.5 cosine of 25. I'm getting 7.70. Let me write that in right here, meters per second. And you'll notice here, because this angle is 25 degrees, it's closer to the horizon. It's closer to the horizon than it is to the straight up vertical. So more of this 8.5 meters per second component will be in the x direction. So we would expect that the y direction will be smaller. Let's calculate it and see. Vy is equal to 8.5 sine 25, and for that we're getting 3.59. If I was doing this on my calculator, I would do this first, then multiply, just so you don't get confusion with your calculator. Let's write that in here. Vy is equal to 3.59 meters per second. I've written them pretty tiny there, but hopefully you can see that for later use. I'll erase this now, and we're going to go to the next step, which is to find the total time of flight. Finding the time of flight for Leo can be a little bit complicated, and basically what we're going to do for this is just simply look at the y component. So here we have the y component. He's going to go up and then he's going to stop and go back down. He's going to have a larger velocity here than he does here. Here his velocity is going to be 0 basically. Here his y component of velocity is going to be vy, which we just calculated here. And we'd like to know his total time of flight. And this distance here is 4.5. We know those things, but we don't know exactly how we're going to solve this. To do that, we're going to need to write out the equations of motions, and I'm going to write them down right here and then just explain them to you really quickly and see which one we might be able to apply in this situation. So here I've written out the equations of motion. These are all for constant acceleration. This one is the average velocity is equal to the initial velocity. Some people write VI plus the final velocity over 2. The final velocity squared is equal to the initial velocity squared plus 2 times acceleration times distance. Also, the final velocity is equal to the initial velocity plus the acceleration times time. Those all deal with velocity. This is the oddball one. It's a little bit hard for us to understand how that comes into being. And then there's one here that deals with the distance something goes. This could be a distance in the x direction. This could be a distance in the y direction. And this initial velocity would be in the direction of the distance and the acceleration in the direction of the distance. What if we can use this equation to model Leo's motion in the y direction, and maybe that will help us to find the time. Let's just write this all out, but with reference to the y. So here's y as a function of time would be equal to the initial y position plus the y velocity times time plus 1/2 acceleration times time squared. And this is the acceleration in the y direction. In a case like this, because the y has direction, it has an up and it has a down, we need to be careful which of these is positive. Well, let's start with the orientation of Leo right up here. Let's start with him right there and go upward. The position with regard to here. We want to find out the position with regard to this. So the initial position here, we're just going to mark that as 0. And then his velocity here is going to be the y component right here, 3.59 times time. And then we're going to subtract, I'll just put that there so I don't have to lean over quite as much here. We're going to subtract 1/2 times 9.8 because that's the acceleration. It's going the opposite direction of the velocity, hence I'm making it negative times t squared. So this would be, we're trying to find out at what time he's in what position. We're trying to find out when he is at minus 4.5 from here. So we're going to make this here a minus 4.5, because this is a model of his position with regard to y. We can make the origin anywhere we want to, so we're going to start it off from here and realize this is where we want him to land. Now we've got this equation here, but notice here I have 4.5. I can move that to this side, and then I have everything on one side and a 0 on the other side. I'm going to erase this, and I'm going to work on that right above here. So since we're going to have an equal sign here, equal, this will end up being 0, and we're going to pull this to this side, making this a 4.5. It's going to be a positive. And then we're going to have this, plus 3.59 t minus this. I'll do this math right away. 9.8 times 1/2 is 4.9, minus 4.9 t squared. Are you okay if I do that right away? Make that 4.9 so I don't have to carry this half all the time. Now I've got this equation rewritten here, but I moved this 4.5 to this side, and it's all equal to 0. Why did I do that? Because I'd like it to look like a normal equation where I can solve it using the quadratic formula. To do that, remember what form we want it in. We want it in the form of ax squared plus bx plus c is equal to 0. Now we're very close on this one, but we have this all sort of reversed. So let's just shift this around so we have it in the same form as over here. And I'm going to make this minus 4.9 t squared. It's t squared rather than x squared, but that's okay. Plus 3.59 t plus 4.5 equals 0. I just moved the 0 to this side just because I ran out of room over here. So now I have this in the form of a quadratic equation. I have a negative here. It doesn't matter. We can leave it there because we're going to use the quadratic formula. But just to clean it up, what if we multiplied everything through by minus 1? In that case, this would become positive, this would be negative, and this would become negative. And then we're multiplying the 0 by minus 1. Minus 1, that doesn't matter. So now I have this all in this form. Notice here, and here, and here, we have the values of A, B, and C. I'm going to write those down here so we have those ready to go, and then we'll use the quadratic formula. Let me erase this now. We can use the quadratic formula as I promised. And the way that you do that is x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. You plug these values now into here. The best way to do that often is to work on this thing first, what's called the discriminant. It's what helps you determine how many roots there are. But in this case, I'm just going to write them all down here so you can see something right away that's going to help you in making the calculation. First of all, let's start off with negative b. Well, this thing is negative, so we're going to make it double negative, or 3.59. And then it's going to be plus or minus the long radical again. B squared, it's a negative, but we're going to square it, so that kills the negative sign. 3.59 squared minus 4. A is 4.9. Hopefully you can see all this. And this is minus 4.5. So there's a minus sign here and a minus sign here. Those will cancel each other out and we're going to get plus. It's all divided by 2a. 2 times 4.9. If you remember before, 2 times 4.9 actually is 9.8. That's where we undid the g. We divided g by 1/2 or multiplied g by 1/2. So now we have this whole thing here. I don't need this and I don't need this. And we can start working our way through this. First of all, take a look at something in here. Notice this is 3.59 squared and then square root. And then there's something added to it. So this term in here is going to be bigger than this term. This is 3.59. This is 3.59 squared and then square root, which is going to make it 3.59. But it's going to be bigger because of this term. So if we use the minus sign, we would get a negative answer for x. Or in this case, it's t. It's time. T. Negative answer doesn't make any sense. It's an answer. What would, what time would Leo sort of be if you're looking backwards on the same equation, if you could draw the same parabola down to here? In mathematics, when you take mathematics and apply it to physical problems, you're going to at times find answers that aren't reflective in the actual boundaries. We're working within the boundary of here to here, not back here. So the negative answer doesn't make any sense. We're going to just remove that right away. We don't need it. Now we can do the math on this. If I was doing the math, I would do this first. I would do this part first, and then the square part, add that, because it's easy to make mistakes in your calculator, and then find out what that is. Let me write a couple of these things down, and I'll show you the calculation. So taking a look at this here, you have all of this inside here, about 101, which the square root of that is going to be about 10. Adding these up is going to be about 14. Divided by 10 is going to be about 1.4. This answer looks reasonable. Always check to see if the answer is reasonable. This would be the answer in seconds. Now notice in our original equation, we have two significant figures, but we tend to, when you do the calculation, here I've kept 3 for the velocities, and I'm going to keep 3 here as well. And the reason for that is because if you drop it down to the correct number of significant figures too soon, you will start having rounding errors by the time you get to the final answer. So let me write this one in here, and we're going to do the last part of this calculation. I've calculated the total time, 1.39, written it in here. That's in seconds. Now we're going to use this equation here. The distance something travels is equal to the initial distance plus the initial velocity times time. There's no acceleration in this direction, so we drop this term. And we're just concerned about the distance that it travels is the initial distance plus the initial velocity times time. Well, we're measuring it right here, so there's no initial distance. So it's just equal to the x velocity times time, and that would be the range. The range is what we've written up here. There's no initial distance, and there's no acceleration in this direction. So we just write it like this. And what do we have for that? We have the x velocity, 7.70, and we have the time, 1.39. This should be about 10. Let me check my calculator. I'm coming up with 10.78 meters. Let's write that down over here. The range is equal to 10.78 meters. Now that's a great answer. It's got 4 significant figures, but notice here we have 2, here we have 2. So if we're going to take this down to 3 significant figures, it would be 10.8. If you're taking it down to 2 significant figures, you're going to say the range is going to be equal to 11 meters. Make sure when you do your final answer, you come up with the correct number of significant figures. Put a box around it or something so you're clear as to which is your answer. So does that seem like a reasonable distance for a lion to jump off a cliff? Well, just think about it. That's about the distance of first downs in football. So that would seem like a lion might be able to jump that. Always ask yourself if your answer is reasonable. If this helped you, like and subscribe, and I will hopefully see you in the next video. Bye-bye.